Okay, you may have seen a lot of this before, but let's remind ourselves about greatest common divisors and the Euclidean algorithm. So let me give the definition of a greatest common divisor first. So let A and B be integers. I think we should say they're not both 0. It's hard to decide what the GCD of 0 and 0 is. The greatest common divisor of A and B is the integer D if the following, I guess if the following two things hold. One, D has to be a common divisor, right? D divides A and D divides B. And two, if E divides A and E divides B, then, so if E is another common divisor, then E is less than or equal to D, right? I mean, that's kind of the standard definition. So this is the common divisor. It has to be a common divisor, and it has to be the greatest among them, the largest. Okay. So that's fairly standard. By the way, notation for this, well, you can just say GCD A comma B, but what people tend to do is drop the GCD and just write parentheses A comma B, which could be annoying if you're also doing stuff in the Cartesian plane because it looks like a point, or it looks like the interval from A to B or something like that. So for example, if you just took like you'll see things like this in number theory books, like parentheses 15 comma 25. Well, it's basically asking for the greatest common divisor of 15 and 25, which I think is 5. Okay. So that's the formal definition. Now, question. What's the most efficient way to find the greatest common divisor of two integers? Or I don't know, most is a pretty strong term. What is an efficient way to find the GCD of two given integers? So one thing you could do, you could list all the divisors of both. Or of each. And find the biggest common one. That could take a long time if you got a very large number with lots of divisors, or you could prime factor both numbers. And take all the common factors, right? For example, just as an example, that if I had like 2 cubed times 3 to the 4th times 5 times 7 squared, and I wanted the GCD of that with 2 squared times 3 cubed times 5 cubed times 7. Well, you can just sort of see, well, okay, each of them has two, has two 2's in it, but this one doesn't have a third 2. This one does. This one has 4 3's. This one has 3 3's, so they share 3 3's in common. This only has 1 5. This has 3 5's. This only has 1 7. This has 2 7's. So you can almost, once you have a prime factorization, you can pretty much just write out the GCD. It's 2 squared times 3 cubed times 5 times 7. I don't care if these numbers equal. I'm just trying to illustrate the point. Right, that you're just basically taking as many primes as you can. That fit in both. So, okay. But again, these could take a long time, especially if you have some number. And what's going to happen in cryptography especially is you're going to have a number that's like a 200-digit number that factors into 200-digit primes. And so to be able to prime factor it in the first place is very, very difficult. So better is what's called the Euclidean algorithm, which I'll illustrate in a moment with an example. But let's remind ourselves of the statement. This is going to use division with quotient and remainder. So let's remind ourselves of the statement of that in the integers, at least. So the statement is the following. So given a and b in the integers, given integers a and b, we don't want to divide by 0, so let's not allow b to be 0. Basically, if I want to divide a by b, I can get a quotient and a remainder. We don't want to really think about the fraction a over b because we're leaving the integers if we do that. But we can say there exists q and r in the integers such that a equals bq plus r. So that's basically like you're dividing, taking the quotient and the remainder. And r, well, it could be 0 if b happens to divide into a evenly, but it's also no bigger than b, or it's smaller than b, right? The remainder is always smaller than the thing you divide by. Just as an example, what 25 is 7 times. How many times is 7 going to 25? 3 times, with a remainder of 4. And 4 satisfies 0 less than or equal to 4 less than 7. Right? The 4 is a remainder. It's smaller than what you divided by. Okay. You can prove this from the axioms. I'd like to post some videos at some point that have some rigorous proofs in them, but I won't do that right now. Okay, but that's a useful thing. So being able to divide with quotient and remainders is helpful. Why? Well, let's do an example. So let me just go to the next page here. So example. And I'll do something fairly small. What if we wanted to find the GCD of 143 and 104? Again, I don't have to write GCD here. I could just write parentheses 143, 104. But, what does that equal to? This is small enough that you can factor it. You could probably find the prime factors and find the GCD fairly quickly. But I just want to illustrate something. So what if we actually do division? So divide 143 by 104. Doesn't look like a 143. So 143 is, well, it goes in once, right? 104 times 1. And the remainder, I think, is 39. Okay. Well, why do I care about this? Well, one thing you could say is that notice, let's talk about a common divisor. If E divides 143 and E divides 104, then E divides 143 minus 104, which is 39. So, well, I guess I'm saying 143 minus 104, which means E divides 39. So, okay, that's something. It's like sort of saying like, okay, if I have a common divisor, it actually has to divide the difference, or in this case, you know, the remainder, and you do the quotient. So that narrows down our search a little bit, maybe. You could say, okay, the common divisor has to be divisor of 39, and that gets you, you know, then you could pretty much be done. But let me, so this was kind of the first step in the algorithm. But now the next step is divide. So let's get rid of the 143. That's the biggest number. Kind of throw it away. But we have these two numbers, 104 and 39, right? And we know basically if there's a common divisor of 143 and 104, then it will also be it will also divide 39. So it's a common divisor of 104 and 39. So let's divide 104 by 39. So 104, let's see, 39 goes into 104 probably twice. I think 3 times is too big. And what's the remainder? 78, 22, 26. Okay. And so our common divisor, right, E divided 104 and E divided 39. So that means E is going to divide 26 because it's 104 minus twice 39. You could sort of think about isolating the remainder. Right, so our common divisor divides 26. Keep going. Now we could throw away the bigger number 104, and we have these smaller numbers 39 and 26. So divide, oh wait, let me circle the, this is the second step of the algorithm that I just put in green. So let's divide, you could probably really see the answer now, by the way, but let's just keep going. Well, okay, 39. Can't I write tonight, guys? 39 is 26 times 1 plus 13. And again, E divides 39 and E divides 26 implies E divides 13. And there's your third step of the algorithm. Again, throw away the larger number, take these two numbers, 26 and 13, divide 26 by 13, and oh, oops. Here's where something interesting happens. And so 26 is 13 times 2 plus 0, no remainder. And so really this just leads us to saying that our common divisor, I mean, in some ways you didn't have to do the step, because once you get to the point where these last two numbers do divide evenly, you can say, okay, well then definitely our common divisors are all divisors of 13. So are all divisors of 13. They all have to be divisor. Maybe I should say it slightly differently. I'm not saying a priori that they are all the divisors of 13. I'm saying that they, turns out that's true, but our common divisors have to be divisors of 13. Okay, but does that mean 13 is a common divisor? We just showed that common divisors have to divide 13. But But that doesn't show, it's kind of a weird thing. It doesn't show, oh, by the way, I should put a box around this. Okay. So it doesn't show, I haven't showed that 13 is a common divisor. I've just shown that if you have a common divisor of these first two numbers up here, then it also has to be a divisor of 13. So 13 is the largest possible, but why is it a common divisor? So I claim that 13, in fact, is a common divisor. Sorry, 13, yeah, 13 is a common divisor of 143 and 104. And because of that, basically these two statements together, the fact that the common divisors have to be divisors of 13 and that 13 is a common divisor, these together would say that the GCD of 143 and 104 is in fact 13, right? Because we know common divisors are at most 13 because they're all divisors of 13. But if we say 13 actually is a common divisor, then it is. Then it is actually a common divisor and it's the biggest one. So why, okay, maybe this seems obvious, but it's actually a little bit different. So the argument's slightly different. So let me recopy the algorithm. So really what the Euclid algorithm for this says the following. Let me just copy these again. Copy. I probably could cut and paste or something if I was fancy, but I think it would take just about as long. Okay, so this was the Euclidean algorithm. These are the steps of the algorithm. And the claim is that actually this last non-zero remainder is the GCD. Is the GCD of the two numbers you started with. And that's actually going to work in general. But why is 13 a divisor of 143 and why is a divisor of 104? Well, what we were doing is we were chasing the common divisors sort of down the algorithm, right? Like if we had a divisor of 143 and 104, then it had to be a divisor of 39, and then we sort of kept going and so on, right? The argument here is actually chasing back up. 13 divides 26. So we know 13 divides 26, and 13 divides itself, right? So that means 13 is a divisor of 26 times 1 plus 13, which is, oh, geez. So 13 is a divisor of 39. I could be doing this all with letters, but I think it's more illustrative if you use numbers. So basically you can convert these all to letters, and use Q's and R's and A's and P's and stuff, but I'm just going to do it with numbers. And then you have, okay, so that was kind of using this row of the algorithm. But now you know 13 divides 26 and 13 divides 39. So 13 is going to divide 104. So this is kind of going backwards. 13 divides 26, 13 divides 39, implies 13 divides 39 times 2 plus 26. So 13 divides 104. Right, and then finally 13 divides 39, 13 divides 104, means that 13 is a divisor of 104 plus 39. So 13 is a divisor of 143. Okay, so 13 is so 13 is a common divisor. So that's why this is sort of nice. Is this actually doing this repeated division and taking throwing away the biggest number, taking the, we took these two numbers, and then we divided and got the quotient and we got the quotient and the remainder. And then we threw away the big number and we took the two numbers here and moved them over there. Did the division again, got a new remainder, threw away 104, took these two numbers, moved them down here, did the division again, and so on. You basically keep doing that. That's what the Euclidean algorithm is. You keep doing that over and over again. And if you just changed all these numbers to letters, you would see that this last non-zero, in this argument that I gave, you would see this last non-zero remainder is actually the GCD. Right here, what I'm saying right here. Okay, so that is a helpful idea. And again, these numbers were small enough, but if you had something that was very large and you couldn't prime factor it easily, I claim this is much faster. And actually, let me just show you that I can give you a good argument that this is much faster. In fact, we could have done this, we could have even done this example faster if we allowed ourselves negative remainders. So an alternative Euclidean algorithm or an alternative division is we can say A equals BQ plus R, but where R is actually between, now you might have to be equal, but it's between minus B over 2 and B over 2. Right? You could take the nearest quotient. Like what we were doing up here was we were taking the biggest quotient, right? Like here with 104, 39 times 2 is actually not the closest multiple of 39 to 104. It's the biggest, it's like the Price is Right. It's the biggest multiple that's less than 104. So you could have done something, we could have done this alternatively like this. 143 is 104 times 1 plus 39. 104 is actually 39 times 3. I can write a damn 3. 39 times 3 plus, so that's actually 117 plus negative 13. Really not happy with the handwriting on these. Plus negative 13, and then 39 is negative 13 times negative 3 plus 0. And so we actually found, well, I guess you get it up to plus and minus, but we actually did this just in 2 steps. And if you allow the remainders, if you allow negative remainders, then what you're doing is each step cuts down the you're cutting down the thing you divided by at least half because you have this B over 2. So each step cuts the remainder down by at least half. So one way to think about this is if you actually wrote up these numbers all in binary, cutting in half would be like cutting off a bit, cutting off one digit. They're called bits, right? You'd actually make it one shorter. And so, the runtime, we'll talk about runtimes of algorithms like later more systematically, but the runtime is, there's at most the number of steps, maybe I should say, the number of steps is at most the number of bits, the number of binary digits, if you wrote these numbers in binary, and in fact, probably even the smaller in the smaller of A and B. And that means that's an algorithm that's really fast. Even if you had like a 200-digit number, it still might only be, what is it? 200-digit number could be like 600 bits or 800 bits or 650 bits or something. So this would take it, even if you had a 100-digit number, this would take almost 650 steps. A computer can do this trivially. And so again, we'll talk more systematically about these runtime of algorithm things, but this is hugely, hugely fast. Okay. Okay, I've said enough. I will stop there.